welcome to all of you in the next class of this course. So, let us summarize what we were doing in the last lecture. In the last lecture, we were trying to evaluate evaluation of scaling function and wavelets. Of course, it is a next lecture, lecture 32. Okay. So, as we have seen that with the help of MRA, phi x will be can be written in the following way. So, phi which is unknown, which is that is available in the left hand side as well as in the right hand side. So, that is why we have to devise some specific algorithms to compute that. And then in the last lecture I have stated 3 methods to compute this phi. First one which I mentioned in the last lecture was cascade method. I will explain the basic idea behind this cascade method, and for detail you could look at in this reference. So, for detail one could refer the reference Strang and Nguyen, Wavelet and Filter Banks. This is the title of book, Wavelet and Filter Banks, and this is published by Springer. This is a book for which you could refer the detail about this method. The basic idea I am explaining here. So, what we are doing? We are writing this in the following fashion. So, we have to start with some phi naught x, that is what we always do in iterative methods. So, we have to start with some phi naught, and then the if phi I x converges to phi x, it will solve the dilation equation. So, that is the basic idea behind cascade method, that you start with some initial guess phi naught x, and with that and then you keep iterating this procedure, and if phi I x converges to phi x, then that will solve the dilation equation, because this is also called the dilation equation, two scale relation that we have already seen in the last lecture. So, and again I am saying, for detail about this method one could refer to the book by Strange and Neumann. Title of that book is Wavelet and Filter Banks, and it is published by Cambridge Press. Okay. So, this was the idea behind cascade method. The next method which I stated in the last lecture was spectral method. Spectral method. So, as the name is suggesting, spectral means we are taking the into the Fourier domain. So, for that purpose I am computing the Fourier transform of this relation both the sides. Okay. I am taking the Fourier transform both the sides. So, for that purpose I am multiplying with this over real line okay. So, this left hand side will give me a phi hat omega under root 2 h k. What I am doing? I am putting 2x minus k is equal to y. So, this will be phi y e to the power minus I omega k plus y by 2, dx will be dy by 2. Okay. So, this will become, whole expression will become h k e to the power minus I omega k by 2 phi y e to the power minus I omega y by 2 dy. Clear to everyone? So, if I am denoting this with again phi hat omega by 2, okay, and this functions I am denoting with h omega by 2, where h omega is given by the formula this. Okay. So, the same scaling relations which I have stated here, I have taken that scaling relation in the Fourier domain with the help of this. So, this is the same relation in the Fourier domain, because I need the help of this relations to define a spectral method. That is why I have derived this in fact. Now, I will keep iterating this way. So, phi hat omega will become okay. So, this will this should be h and then phi hat of omega by 2n. Okay. So, if now I am taking as n tends to infinitive, n tends to infinitive. So, for that reason I have to make sure that this product converges. If this product converges, what will be this expression as n tends to infinitive? This will become 0. So, but I have to make sure that this converges, only then I can write this as this way. Okay. So, that I can check from here whether it converges, because this is a project. So, we know h omega, if you look at summation of h k by under root 2, okay. And later on we will see that summation of h k is equal to under root 2, that we will do later on. So, if this is true, then this is less than 1. So, under this condition we can say that this product will converge, and if this product and what is phi hat 0, and we are making one more assumption that on phi, that integral of phi x dx is 1, because this is that phi hat 0. Okay. So, these are two extra assumptions we have taken, which we will see later on. Summation of h k is under root 2. After using this assumptions, we can say that if we compute phi hat 0 is 1. So, if we compute the inverse Fourier transform of this expression, that will give me phi x. Okay, that will give me a inverse Fourier transform of this expression will give me phi x. Okay. So, this is the another method of computing phi x with the help of a Fourier transform. That is why it is called a spectral method. So, we have seen cascade method, their basic assumption was using the iterative algorithm and then converging, and but here also we are using iterations, but in the Fourier domain. So, that is the idea behind spectral method. The another method which I stated in the last lecture was recursion method. It is known as a eigenvalue method, because at the end we have to compute the eigenvector. So, basically it is a eigenvalue problem. Okay. So, it is known as a eigenvalue method, because in this method at the end we have to compute the eigenvector, and that is known as a eigenvalue problem. So, I will show you the detail of this method later on with respect to Dau-Bechi's compactly supported wavelet. Okay. So, that I will explain later on. So, now what I wanted to say, that if this is the relation I have been keep writing. So, this is the main relations. So, with the help of this relations I can compute phi, okay, with the help of any one of the method. Of course, recursion method I will compute later on. So, now if so far I have given you example of a only one wavelet, because if you remember when I was discussing about this multi-resolution analysis, I said phi x is a box function, okay, box function which was 1 in 0 1 and rest where it is 0, and with the help of that box functions we also wrote this relations, if you remember. This was a graphical observation I could say, or because we were knowing the analytic expression, but as I am keep saying that in most of the wavelets we do not have an analytic expression for phi. So, the only way to compute phi is with the help of this relations. So, there are three ways to start, either all of them are equivalent, either you choose HK filter coefficient first, then you can compute phi and then you can compute approximation spaces Vj, or you choose phi then you can compute HKs or Vj. So, means there are three ways to start the multi-resolution analysis. One is choosing a scaling function, another one is start with the filter coefficient, and third one is you start with the multi-resolution scaling spaces Vj itself. So, what are the three ways? One, you start with phi x scaling function, second you start with HK filter coefficient, and third you start with scaling spaces Vj. Okay. So, that is how you could start with the multi-resolution analysis. Okay. So, now as I am saying that analytic expression is not available to us. So, how one could look at this whole construction, and in fact, I have said that recursion method I will explain later on. So, for that reason now I am going to define a new category of a wavelet which is called Dau-Bechi's wavelet. I can say it is the most popular wavelet so far. Of course, it has couple of disadvantages as well, and that is why we are also now going into the domain of another wavelets. But just to start for a beginners, it is a good wavelet, I could say. So, Dau-Bechi's was the first one to use this MRA theory invented by Stephen Mallet and Meyer to construct a compactly supported wavelet of some smoothness. So, okay. So, what Dau-Bechi's did, she used this MRA theory to construct a compactly supported wavelet, to construct compactly supported wavelet. That was his, not his, that was her contribution. Okay. So, how we were defining compactly supported wavelet with respect to scaling functions and wavelet. Okay. So, here 0 to infinity and psi x is also, sorry, k is minus infinitive to infinitive, and this is because wavelet system is characterized by phi and psi. That is why in the last topic when I was computing phi, once you know how to compute phi, you can also compute psi. So, that is why I have not written separately how to compute psi. So, now this is the relation for phi, this is the wavelet equation, and this is dilation equations. Okay. Okay. So, now what she did, she said that if finitely many HKs are non-zero, then phi and psi are finitely many HKs and GKs are non-zero, then it is a compactly supported wavelet. In fact, I have stated this definition of a compactly supported wavelet in my last lecture as well. So, in case of a compactly supported wavelet whose order is defined by D, compactly supported wavelet whose order is defined by D, which is also D is the D we can call order of wavelet as well as wavelet genus. Okay. So, we are defining phi x will be similarly in psi x also we can write down here k is minus infinity to infinity, but for a compactly supported wavelet we can write down k is from 0 to d minus 1. Okay. K, so, d is order of the wavelet. Okay. Of course, as psi is related, and this one could prove that this GK and HKs are also related by the following relation. Okay. GKs and HKs are related by the following relation, where k is from 0 to d minus 1, d is the order of the wavelet, or you could also call it as a wavelet genus. For a proof of this, how these are related, one could look at the reference by book 10 lectures on wavelet, 10 lectures on wavelets by Ingrid Daubechies. Okay. I have also given you the reference where you could see this. So, now as I said that we have to look at how to compute first, if we are starting with the filter coefficients, how to compute this HKs and GKs. Okay. So, for that reason I could say that okay, when I was defining a phi x as a box function, then I have stated this results, if you remember from the last lecture. So, basically H naught was 1 by under root 2, H1 was also 1 by under root 2, and when I was writing psi x with the this relation, I was writing G0 is 1 by under root 2 and G1 is minus 1 by under root 2. So, you can cross check this relation will be satisfied for these values of H and G, that you could check, that you can take it as exercise and you could check that this relation should be satisfied. So, and what will be the order of this wavelet? Because then order of this wavelet will be 1, okay, because only H naught and H1 are non-zero. Okay. So, this is first family of a first member of the Daubechies family. So, the wavelet which I defined in my last lecture with the help of an analytic expression is a first member of Daubechies family. First member of Daubechies family. Okay. It is also called Haar wavelet. It is also called Haar wavelet. Fortunately, when we were constructing a wavelet of Daubechies family, we ended up that when we are saying d is equal to 1, it corresponds to scaling function corresponds to a box function and wavelet function corresponds to this kind of a functions which I have stated in my last lecture. So, that was also a Haar wavelet. Why it is called, why its name is also a Haar wavelet? Because Alfred Haar is the name of a scientist who separately discovered this as a basis function. Okay. So, that was the idea. Now, I am saying if you could say that the box function was having a support in 0 1 and the wavelet Haar wavelet case phi and psi both are having a support in 0 to 1. Okay. So, basically if I wanted to generalize this idea, I could say that for a Daubechies wavelet of order D, phi and psi support of phi and psi will be this, you could say, okay, or maybe what you could say that support of phi is equal to support of psi is equal to 0 to d minus 1. Okay. Clear? Daubechies wavelet of order D will have support both scaling function and wavelet function, because every wavelet is, or in fact I should say wavelet system is characterized by two function phi and psi. Phi is scaling function and psi is wavelet which are constructed by MRA. Okay. So, support is 0 to d minus 1. So, if now if I am saying what will be the support of this function which is dilated by 2j and translation by k. So, the support of this function you could also define this way, support of will be ikj, where ikj is basically k by 2j, k plus d minus 1 2j. Okay. So, this will be the support of phi kj and psi kj if support of phi and psi is given by this 0 to d minus 1. Now, I will tell you how to compute this filter coefficients for a general order D wavelet. In the previous slide, we have computed HKs and GK not in a general way, because we were knowing the analytic expression for phi. So, that is why either from the function or from the graphical representation, by observing we have computed HKs and GK. Now, I am telling you the method to compute HKs and GKs in a general way for any wavelet of whose order is D, and it comes under the Daubechies family. So, of course, you will be needing some specific set of equations. So, for HKs to compute that. So, what I am doing for that, numerical evaluations of H case and G case. Okay. So, of course, again I have to write this results k is 0 to d minus 1. Okay. So, that is why you know MR is the heart of a wavelet theory, because you can see every time I am keep using the same results. So, if I am integrating this in the both sides, okay, minus infinitive to plus infinitive, minus infinitive to plus infinitive. Okay. So, as I have said that I will be stating one condition, that integral of phi x dx is 1. So, this is under root 2 summation of h k. So, if now I am putting 2 x minus k is equal to y, this will become phi I and dy by 2. So, summation of h k will be under root 2. So, this is the results which I used earlier, and I said that I will prove it later. In fact, it is not specific to k is equal to 0 to d minus 1 only for compactly supported wavelet. In fact, if you would have written k is from minus infinity to infinitive, then also it is true. That is why we were able to use it at that point of time, where we were not defining just compactly supported wavelet, we were driving a family of the wavelet in a general sense. Okay. So, integral. So, this is one of the results we are getting in case of a, of course, here I have to make assumption that k 0 to d minus 1. So, now this is just if I wanted again, okay, whatever computations we have done in case of a Haar scaling function and wavelet earlier, by observing the function I can show you here also. So, if d is 1, this will become h 0 plus h 1, sorry, d is 2, d is 2. Okay. So, h naught plus h 1 will become under root 2. Okay. If this is the case, here also it should be d is equal to 2. Okay. Then it will corresponds to Haar wavelet. Now, but we cannot solve it for Hk, we need some additional conditions as well. So, for that reason I am stating another assumption which we have anyway we have already made, that phi x minus k forms an orthonormal basis for a space V naught. Okay. So, this will be phi x minus n dx when n belongs to Z. This is the relation we know from MRA assumption. So, now I am using again two scale relations. Here I am taking a index L, okay. So, this will become 2 summation of k is 0 to d minus 1 h k, okay, and another summation will be on L h L, okay, and then this integral will become phi 2 x minus k phi 2x minus 2n minus L into dx. Clear to everyone? So, now I am saying that this 2x minus k is equal to y. So, if this is true, I can copy the same thing here. What will be the value of this integral in that case? 5y, and 5 will become y plus k minus 2n minus L dy by 2. Okay. So, this 2 we can cancel from here. So, finally, this is summation over k, this is summation over L, hk and hl, and this function will become, if you remember, 5y and this y plus k, and this should be 2n. Okay. So, this will become 5 y plus k minus 2n minus L dy. So, I can write down this in the form of a delta function, k minus 2n into L. Okay. K minus 2n into L, that is why, because it is the assumption of MRA that it forms a orthonormal basis. So, if this is the idea, and whatever non-zero terms I will get, that I can write down in this form. H k minus 2n, n belongs to Z, where k1 n will become maximum of 0 to 2n, and k2 will become minimum of d minus 1 plus 2x. Okay. So, there are, you could get as many equation as n belongs to Z, but there are, you can observe that you will get only these many distinct equations. Okay. So, what I mean to say that k minus 2n, where n is 0, 1, 2, these many distinct equations you will get, okay, after using this MRA assumptions. So, if for d is equal to 2, Haar wavelet n is 0 to 1. So, basically you will have h naught square plus h1 square is equal to 1. So, which is a non-linear equation you could observe, and the other equations which I have written earlier was this. So, after solving both of them, you could say h naught is 1 by under root 2 and h1 is also 1 by under root 2. So, this was in the case of just specific d is equal to 2, which corresponds to Haar wavelet. Generally, from here how many equations, distinct equations I have mentioned here, d by 2, and what is the non-zero value of the filter coefficients you have to compute? Total h naught, h1 to this h1 and h d minus 1. So, total you need d equations, d by 2 distinct equations you got from here, 1 equations you got from here, if you remember. So, 1 equation from here, d by 2 from here. So, total we have d by 2 plus 1 distinct equation so far. Okay. So, and how many equations I need? I need total equation should be this D. Okay. So, I need remaining equations. So, from where I will bring this remaining equations? I am bringing this remaining equations from one of the fundamental property of the wavelet which I have stated in previous lecture, that was vanishing moment property. Vanishing moment property was saying that xp psi x dx is 0 when p is 0 to m minus 1, and this is the relation we have with m and vanishing moments. M is d by 2, or basically d is 2m. D is called the order of the wavelet in case of a Dau-Bechi's wavelet, and m is vanishing moment of the wavelet. So, for a Haar wavelet, d is 2, m is 1. So, vanishing moment is 1, order is 2, and from this relations one can construct this. Okay. For p is 1, 2. So, from here I got these many distinct equations. So, if you add this term and you add this term, you end up with these many equations. That was the goal, because if I to have a unique solvable system, I should have a same number of a linear equation as same number of a unknowns, that all of us already know from numerical analysis course, or you could say linear algebra course. So, that is how, you know, from the assumptions of MRA one could see how to compute this filter coefficients. In fact, you do not need to go through all this algorithm, because there is a inbuilt MATLAB function which is W filters in the MATLAB, which gives you a filter coefficients for a wavelet, which you write down here. So, this is the syntax of a MATLAB function which I am writing. Okay. Suppose all of you know MATLAB, and if some of you want to try to implement wavelet in the numerical method or a wavelet in any other field of applied mathematics, first of all you have to know how to start with it, and this is the first step, because the most simpler wavelet is Dau-Bechi's wavelet, and this is the simple. So, if we should know how to start with the Dau-Bechi's wavelet. So, first what we have to do, we have to compute the filter coefficient. So, for that there is a inbuilt MATLAB function W filters, which computes this low pass filter coefficient Hk's and high pass filter coefficients, and this is the name of the wavelet you have to give. But right now we have just seen only one kind of a wavelet, Dau-Bechi's family of the wavelet. So, that is why we can write DBM, but later on if you know any other wavelet also, that name also you can write this in a single quote, and iteration is the parameter which one has to use, that in the syntax of the computation. Okay. So, DBM means M is Dau-Bechi's, DB stands for Dau-Bechi's, and M is the vanishing moment. So, in case of a Haar wavelet, what you will write? You will write DB1. Okay. So, if anyone wants to know the information about this function, they could you could type in the MATLAB wave info, okay, DBM. It will give you a complete information about Dau-Bechi's wavelet. Okay. The inbuilt function is wave info. If later on also we study some another wavelets, we can type wave info, and that the name, of course you should know this short form of it before typing, otherwise how can you type it, wave info dBm, it will. So, one can try if you want to know more about this category of the wavelet. Okay. So, if I give dB 1, then you could see H naught H1 should be 1 by under root 2, 1 by under root 2, and G naught G1 should be 1 by under root 2. And so, what is the results of dB 1 should come? Results of dB 1 should come this way. Okay. So, if you look at general order wavelet, so in that case let us say dB 2, so it means M is 2, D is 4. So, how many filter coefficient will be non-zero? 4. So, you will have here H naught, H1, H2, H3. GK will also be G naught, G1, G2, G3, and the value of this HKs and GKs you could compute from this inbuilt MATLAB function W filters. Okay. So, by this time all of us should feel very comfortable how to compute this filter coefficients. Once filter coefficients are known to you, you can compute the value of phi and psi with the help of a dilation equation and wavelet equation. Okay. Because if you remember, initially I have talked evaluation of scaling function and wavelets. That was with the help of 3 methods: spectral method, cascade method and recursion method. And recursion method I said I will explain later. So, this is the time I can explain you the recursion method to compute phi and psi. Recursion method. So, what this method does, we know if phi and psi is a Daubechies family wavelet whose order is D, then support of we know support of phi and psi will be D minus this. Okay. So, this is also proved in the book of Ingrid Daubechies, 10 lectures on wavelet. If phi x suppose phi 0 means at the end point it is 0 for D is greater than equal to 4. Okay. This relation is in the book of 10 lectures on wavelet by Ingrid Daubechies. So, we will be using this relation in recursion method. Okay. So, what we are doing, we know this thing. Okay. So, this we will be putting the x1 to d minus 2. We will putting this value of x in the following relation. So, if we are taking, let us say, let us start computing after taking this d is equal to 6. So, if x is 1, phi 1, because you know we are not interested in phi 0 because phi 0 is already 0. So, phi 1 will be equal to under root 2 summation of h k phi 2 minus k. Okay. Similarly, if so for d is equal to 6, I will be keep substituting. So, this corresponds to x is equal to 1, x is equal to 2, 3, 4. Okay. So phi 2 will become 4 minus k, phi 3 will become 6 minus k, and phi 4 will become 8 minus k. Okay. So now, and k is varying from 0 to d minus 1, k is varying from, in each case k is varying from 0 to 5. So now this you can take it as a homework exercise, you expand this and then finally we will be able to write this as a phi 0 is basically a naught phi 0. So this is a vector where phi naught is basically, if you, the value of phi at 0, phi, no sorry, 1, 2, 3 and 4. Okay. Because we have taken d is equal to 6, so we will be computing for this vector. So what this problem has become? If you look at, this is this problem. Can you relate this problem to the problem of linear algebra? Of course, it is a eigenvalue problem. As I have said that in a recursion method, it is known as a eigenvalue method, because at the end we have to compute the eigenvector. So basically phi, this vector is a eigenvector, corresponds to which eigenvalue? Corresponds to eigenvalue 1, because if I can write down this way, this is a eigenvector I or phi naught. So this is eigenvalue problem. We know how to compute a eigenvector corresponds to any eigenvalue. So if you know that, you know how to compute this vector. Okay. Of course, for that reason lambda should be eigenvalue of this matrix, that you can check and you can take it as exercise. 1 is the eigenvalue of this matrix A naught, and what is the entry in the matrix A naught? A naught will be a matrix which will contains entries of a low pass filter coefficient, because that is how you could see this is low pass filter coefficients. Okay. So phi naught is a eigenvector corresponds to eigenvalue 1 of matrix A naught. Okay. Phi naught G eigenvector corresponds to eigenvalue 1 of a matrix. Once you know the value of phi at some integer points. Now you start substituting x is equal to half, 3 by half and 5 by half, because if you remember we were trying to put earlier x 1 to d minus 2 and d is equal to 6. So we are putting this value, then we can compute the value of phi at this grids, phi half, phi 3 by 2, 5 by 2, because 7 by 2, 9 by 2. Okay. So then basically you could denote this as a this vector okay, and this whole then this will become this matrix. Again A1 is a matrix which contains no low pass filter coefficients. This is eigenvector we know. So, if we know this, we can compute this. So, you can keep iterating this procedure to compute the value at any Dydic grid, to compute the value of phi at any Dydic grid. Okay. So, now it is not Dydic, let me say again, we are taking for computational efficiency, you could take any other grid also, but here for computational efficiency we will be using only for a Dydic grid. Okay. So, once you know phi, you can also compute psi at the Dydic grid, because that also can be given by this relation. Okay. So, means you can compute at any grid, or for computational efficiency we are saying Dydic grid. So, initially we will compute phi, phi is known to you, GKs are known to you, then you can compute psi at any m by 2q Dydic grid. So, but I have explained you the algorithm how to compute phi and psi, but if you want to implement, it is up to you, you can implement it also, and there is a inbuilt MATLAB function also. What is that inbuilt MATLAB function says, that I will explain in the next lecture, but there is a inbuilt MATLAB function which is called wavefun. Okay, which will compute the value of phi and psi at the Dydic grid for you people. You do not need to implement this algorithm. That is the beauty of this inbuilt MATLAB function. But really, before using the inbuilt MATLAB function, you should be knowing what it is doing, or what is will be its computational cost. So, for that reason you should know what is the algorithm they will be invoking. So, recursion method basically, if you look at use eigenvalue, you can consider it as a eigenvalue problem. So, thank you very much. That wavefun function I will explain in the next lecture.